Thank you for joining the eBeam initiative, where I'll be going over the full reticle curvilinear inline linearity correction, including variable bias with zero turnaround time. This information was presented at the PMJ finale. This is the extended presentation format, so it's a little bit longer than the material we presented in the main session. This is a collaboration between D2S, NuFlare, and Micron. To start, we'll go over the introduction to the background of what Micron's been doing to explore curvilinear features, the challenges of mixed feature linearity, reducing MPC cost, PLDC-MPC results on Manhattan patterns, PLDC-MPC results on full reticles, PLDC-MPC results on curvilinear patterns, and finally, a forward look to the application of PLDC-MPC on high NA, followed by a brief conclusion. So last year, Micron adopted a new logo, you saw it in the title slide, and slogan. I think this is very appropriate for this talk. That slogan is ahead of the curve. So as many of you know, Micron has been investigating the benefits of curvilinear processing to both low NA EUV and DUV designs for some time. From 2002 to 2024, Micron has reported the advantages of curvilinear designs over Manhattan designs in 3 separate venues. One of those is right here on the eBeam initiative with the curvilinear masks in memory designs from DUV to EUV. And then at the Bacchus keynote, we shared some information about how those results need to be improved and the processes that need to be improved at the mask shop itself. And finally, we shared this also at the ASML Tech Conference in 2024. So this is sort of the background of why we've been looking at curvilinear. First, we'll show an example of the positive impact of curvilinear versus Manhattan methodology on the usable process window on wafer for an advanced DRAM layer. The graphs shown here show the maximum focus window at a given exposure latitude for 2 different CD measurements. So you see CD measurement number 1, CD measurement number 2, CD measurement number 1 and CD measurement number 2. And the area of those 2 curves is the process window. You can see that when we go from a Manhattan pattern to a curvilinear pattern, the process window increases significantly. It more than doubles. Everything gets better. You have better nils, better overlapping dose latitude, and better local CD uniformity. So with the challenges of continuous scaling, you need multi-beam writers for curvilinear patterns, and now you need mask process corrections, or MPC, to improve this as well. Talking about local CD uniformity for a second, with EUV, LCDU impacts wafer LCDU much more directly than it does for DUV. So here you can see a normalized mask LCDU to a normalized wafer LCDU graph. It's not necessarily a one-to-one relationship, even though that's what this shows. This is a normalized feature. But the idea is that mask LCDU is very directly related to the wafer LCDU. Because there's a very direct transfer, this is another driving factor towards curvilinear to get more consistency in the shapes on mask. On the right graph, you can see that wafer CD variation improves with curvilinear or oval shapes. So you can see that this solid line at the bottom represents the oval contact versus the dotted line represents the rectangular contact or Manhattan. So this improves variation through dose and mask bias across the board. Curvilinear is always better. So we can see the advantage of curvilinear shapes in the SEM images as well. You can see visually that they're more uniform. So we need mask process improvements to reduce local CD variation, and curvilinear is a way to do that, but it comes with additional challenges, such as improved resolution, linearity effects on curvilinear features, corner rounding, and dealing with feature-to-feature imbalance. The key message is that to improve local CDU, we must work harder to optimize the EUV mask process and spend time innovating on what was needed compared to optical masks. So that's a lot of the motivating background behind this work. And then as a quick forward look, we can see that high NA anamorphic design will increase the curvature of given DRAM array targets, since it's naturally anamorphic and will naturally add curvature. So linearity, or critical dimension error driven by size and pitch, needs to be corrected. The graph shown here represents error in a mask making process across exposed line space features, unexposed line features, exposed contact holes, and unexposed pillars. The mask maker is tasked with providing features that meet the design targets as closely as possible. Feature design error, or variable etch bias, is a strong function of feature design size, so feature design size, and feature pitch. Variable etch bias is unique to the combination of resist, develop, and etch effects used when processing a photomask. With the advent of EUV, small design features have become more prevalent on reticles, exacerbating the need for some type of mask process correction. So you can see here, I'll use the unexposed line as an example. You can see through pitch at a given design size, you have a large amount of error. This needs to be corrected if you have a large feature mix on the reticle itself. But one thing I want you to think about as well is that as you go to curvilinear features, this doesn't just represent the feature mix across a reticle. This represents the feature mix across a feature itself. We'll talk about that a little bit more later. This chart represents the data flow at the mask shop. MPC occurs as part of the data flow after fracture. Traditional Manhattan data can be processed through MPC as a single step without additional processing. However, this step does incur cost and complexity. Current Manhattan production EUV patterns take approximately 7 hours of processing on cloud. For those who are unfamiliar, cloud computing is renting space on another company's computer rather than having dedicated on-premises clusters. Curvilinear designs require additional cloud computing steps beyond MPC. Each of these steps will be explored in more detail on the next slide. Design data comes over as any angle polygons that represent the design. Today, for manufacturing environments, even if multigon is used for the design, conversion to polygon is necessary for offline MPC, as no vendors support full reticle curvilinear MPC solutions. So the design has to come over as piecewise linear or any angle polygons. These come over as very dense polygons and are regenerated or smoothed to reduce the polygon count to decrease the processing time for MPC. So this is a very dense any angle polygon, and it's smoothed, or the vertex count is reduced to come over here. Since MPC occurs at every vertex, high polygon count incurs high computation time. Without smoothing, MPC would be far too long. The additional cloud computation time for smoothing is on the order of hours. After it's been smoothed, it's now ready for offline MPC. Offline MPC moves the edges locally and adds polygons to produce more accurate contours on the mask. This requires cloud computation and has an additional cycle time of days. For the most complex orders that required MPC, cloud computation required tens of thousands of cores through Micron's cloud service provider. With compute-intensive processes, these calculations took days and incurred very high costs. So we've talked a little bit about the cost in terms of dollars of the cloud computation cost, and in terms of cycle time, the hours and the days of smoothing an offline MPC application. But I'd like you to think about the fact that the highest cost for offline MPC is actually opportunity cost. One thing that sits in my mind as a use case is in 2018, when I had first joined the mask shop, we had an order for a customer to win a customer contract that required us to turn a reticle in 48 hours. Now, for those of you familiar with VSB and multi-beam write times, that's a large chunk of that budget. If we had had to apply offline MPC as well as the write time, we would not have been able to ship that reticle in that time and win that customer contract. That customer contract, of course, is worth hundreds of millions of dollars. So the cost isn't necessarily the cycle time. It's not necessarily the actual cost of the license of the cores. The cost is the opportunity cost to your business to win customer contracts as you need them. A lot of you also see this barrier as well. So in 2024, at the Bacchus survey results, the eBeam initiative shared that the #1 concern for curvilinear adoption is the mask software infrastructure. So a lot of you agree with this perspective. This leads us to a question, which is, can the cost and complexity of offline MPC be eliminated while maintaining CD accuracy? Pixel level dose correction enables a shortcut to MPC'd designs. Multi-beam writers function by having an array of beams exposing areas of patterns simultaneously. The stitching and overlap of these beams to create pixels is fundamentally a rasterizing process. Regardless of the MPC process, a figure must be rasterized into pixel space. NuFlare technology and D2S have proposed that rather than perform MPC corrections in vector space, which must then be pixelated, perform the computation in pixel space. This computation has the additional advantage of converging on a final MPC solution using the dosing information of the pixels directly. Conventional offline MPC does not know the dose regime in pixel space for the process used. So just to reiterate, you go, instead of rasterizing from your post vector space into the pixel space and writing, you can simply skip that, go directly from the design, and using PLDC-MPC, apply the correction in the pixel space in real time. This is the proposal of PLDC. So how does PLDC-MPC work? There's 3 models that work in unison to provide correction. The first is a very conventional beam blur model. This could be thought of as a dose model. So you have your proximity effect corrections and middle effect corrections. Middle effect corrections are shorter range than PEC. They involve the backscatter from the EUV multilayer substrate. And then there's also a shorter range forward scatter blur component through the resist as well. This works directly with the edge dose enhancement model. This is increasing the edge dose at the dose at the edge of a feature to have increased contrast. This increased contrast reduces your dose latitude, thus decreasing your local CD uniformity. By working directly with the beam blur, this dose model is physically modeled well. And then any residual error is modeled by a geometric variable etch bias model. So this uses exposed and unexposed features. So exposed shown here in blue, unexposed in white. There are 2 radii, one on the exterior area outside the exposed feature, and one on the interior area of the exposed feature. This then produces a geometric bias correction based on the feature mix type present within the field. So all 3 of those work together to provide your pixel level dose correction MPC model. How then is it applied? PLDC is applied to the mask during writing. So PLDC is applied to every written field on the mask. And as the mask data is rasterized into the pixel space, the calculations from the previously discussed models are applied, and the modified data is applied to every structure within the field of view. How is PLDC-MPC verified? Traditional MPC can be checked in the data either by visual XOR or a rule-based XOR. PLDC, which happens inline, requires a different approach. Pixel maps of individual CD sites can be compared, but it's not necessarily meaningful for the viewer. I'd like to ask, for these two pixel images, would you know which was correct simply by looking at the pixel map based on the design above? Emulation software is available to show in vector space the predicted contour placement. We'll go through an example video on the next slide. So this is an emulation workstation that D2S can provide to perform XORs on various platforms, either pre-run or post-run. To start the emulation, you can load your data into a workstation. This is a typical contact array pattern for DRAM design that's going to be analyzed. This emulation rasterizes vector-based or curvilinear format from vector space into pixel space and back. Of course, in the multi-beam, you only have to rasterize once. In the case for this rasterization, this red contour shows the simulation of what you would expect the rasterized version to look like without any correction. Of course, you wouldn't write like this. You would write with MPC or some bias modification, those sorts of things. But this is just as an example. Then you can push the dose plus linearity button to apply the PLDC plus dose model with uniformity enhancement to correct the linearity. This is a way to load your specific process into the simulation. We're zooming in to see the difference between the rasterization in red and the green at the very tip of these contact arrays. If we zoom in, we can see the green better, and it's very close to the design. You can then take a cut line to examine the midpoint of the feature of interest and calculate the CD difference. We'll go over these specific numbers a little bit later, but you can select between the design, the rasterization, so this would be the error of your process from the design error, and pixel level dose correction as well. This is constantly loaded into the workstation and overlaid so you can compare all of these examples directly. So one thing that we're also going to show is the dose variability band. So we're going to turn the dose variability band on, and we're going to zoom in to the tip of this feature. The dose variability band is essentially the plus or minus 10% dose for a given feature. You can draw the same sort of cut line through the tip of this, and you can see what plus or minus 10% dose variability would be. You can see that there's a 3.125 nanometer band for red or no correction, and then you'll see a 2.5 nanometer difference in dose variability for the green. This shows the user the expected improvement in dose margin at the edge using the dose model or the reduction in dose latitude. Finally, we're going to zoom out, and we're going to show that this simulation is applied everywhere within the loaded clip. So if you had something besides a DRAM array, such as a logic pattern, you'd have it applied to every feature within the clip that you examine. So now that we see the emulation, what do the actual on-mask results look like? Micron Mask Technology Center exposed a test module after extracting a model to characterize variable edge bias with the following conditions: with edge dose enhancement on, with offline MPC plus edge dose enhancement, and with full inline PLDC-MPC applied, using the dose model, the edge dose enhancement, variable edge bias model. So you can see here some of the test patterns that we examined. First, we'll look at inline MPC versus offline MPC. So for this clear line, this is a clear exposed target. So this is the clear exposed line here. The baseline error range between various design sizes was examined through various pitches. The CD range or the MTT error range for this process is considered the baseline range for the error. Reducing this as much as possible is the goal of MPC. So 3 separate offline MPC vendors were examined. The error baseline range was reduced between 42% to 21% for 3 separate vendors. Inline PLDC range reduction versus baseline was 67%, exceeding the best performance of offline MPC. For dark unexposed lines, so the unexposed lines here are the examined features, the same methodology was applied. So the range of the design and pitch was taken, offline MPC was applied, and the error range reduction is what we looked at. So we saw a reduction of 68% to 50%, where PLDC-MPC reduced the baseline by 81%, again, exceeding the best offline model performance. For whole space, exposed features, so the exposed holes here, the baseline range was obtained, offline MPC was applied, and we see that there was a reduction of 57 to 44%, and PLDC-MPC reduced the range by 67%, the best performance compared to offline models. For dark unexposed pillars, so these dark pillars that you can see here, the baseline range was obtained, offline MPC was applied, and here we see a reduction of 69% versus 54%. In this case, inline PLDC only reduced the baseline error by 38%. So this was the only case where offline MPC performs better than PLDC-MPC. As a summary of these results, PLDC-MPC outperforms offline MPC in 3 categories. No offline MPC model led offline results in more than 2 categories. So you would have to mix and match offline MPC models to get the best results, which isn't necessarily practicable. So no vendor was a clear winner here, where PLDC-MPC was the best for 3 categories. Finally, we're going to look at a full reticle production pattern. So we took a full reticle and applied PLDC-MPC to the features. You can see here that we have 4 main CD features compared to 2 SRAF CD features. The uncorrected version shows what it would look like if no offline MPC was applied. So this is a simulation because obviously we would not do this in real life. But we can see that PLDC-MPC corrects this very well, as there's no error through main CD versus SRAF CD size. So it works well on the full reticle as well as the test clips. This eliminates legacy processes currently done on cloud. It simplifies our data processing and dosing automation. Local CDU improvement from the variable etch bias model. Shown here are mixed features within a CD-SEM field of view showing CD variation. PLDC-MPC reduces this total range. So here you can see the no PLDC-MPC range of these 4 CD sites, CD site 1, CD site 2, CD site 3, CD site 4. And you can see that this error is reduced with PLDC-MPC. Global CDU also improves. So the full die global residual error is reduced by 24%. This is the residual error after correction. Our POR correction is normalized to 1, and we see a 24% reduction compared to that. Finally, the biggest talking point here is write time. The total write time of PLDC-MPC is matched to no MPC. So PLDC-MPC correction truly has 0 turnaround time during processing. You can see here 3 separate writes of the full reticle. The 3 in gray are no PLDC-MPC applied, and then purple is PLDC-MPC applied. This is the delta from the average write time. So the write time of the 3 no PLDC masks were taken, and the deviation from that was calculated. We see about a 1.8% deviation, which is within the noise of the other layouts. There are corrections run to run, which change the layouts. So this is within the noise of that run to run variation. So PLDC-MPC truly has 0 turnaround time during processing, thus shortcutting thus answering the question previously of can the accuracy of CDs be changed with shorter time? The answer is yes. How does it look on curvilinear test patterns, as well as Manhattan structures? So to characterize curvilinear patterns, we used a sine wave structure. We evaluated two different wavelengths. The ratio of achieved amplitude to design amplitude was termed the signal transfer ratio. And signal transfer ratio improvement from variable edge bias versus traditional edge dose enhancement only is what we're comparing here. So we compared concave exposed sections versus convex unexposed sections and took the signal loss of both of those separately. So in this case, all design amplitudes are 160 nanometers. We evaluated 320 nanometer design amplitude, 320 nanometer wavelengths with the 160 nanometer amplitude. For the first algorithm that we had with PLDC-MPC, we saw a transfer ratio of 93% without correction and 92% with correction. So hardly any variation. And this was also true for the 160 nanometer wavelength. Hardly any improvement for the convex features. However, when we discussed this with D2S, they provided an updated algorithm. So the initial algorithm only showed 81% transfer ratio, whereas the updated algorithm number 2 showed 98% transfer ratio. So we went from 127 achieved to 158, a significant improvement. This shows that PLDC-MPC models are tunable, and we suspect that this will also fix the weakest part of the Manhattan data, as this algorithm should also improve those unexposed darks. For concave features, on the first algorithm, we did see improvement. So for the 320 nanometer wavelength design, we saw a transfer ratio of 97% without PLDC, and this was fully corrected with PLDC-MPC when algorithm number 1 was applied. For 160 nanometer wavelength, there was a 86% transfer ratio, and this was almost fully corrected to 98% when we used algorithm number 1. When we went to algorithm number 2, since we have to use the same algorithm for convex and concave curvatures, we saw a transfer ratio of 87% or 139 nanometers of achieved amplitude. When speaking with D2S, they think that they can improve this even further, so you don't have to pick and choose algorithms based on bright field, dark field curvatures. So that's encouraging. We'll continue to evaluate those algorithm tunings. When we look at curvilinear design edge placement error on a true M-bit or memory bit, which is a term that Micron uses when we look at specific contacts in a DRAM pattern, we see a 44% reduction when we apply PLDC-MPC versus no MPC. So this shows the curvilinear pattern, and we can see that there's a 44% error reduction of this M-bit with versus without. So this is showing very good feature-to-feature balance within a specific feature. So at the beginning, I talked about you have feature mix on curvilinear patterns. So here you see a small dark. Here you see a large dark. Here you see a small clear. Here you see a large clear. MPC has to be able to correct all of these equally within the same field of view. And this is showing that PLDC-MPC is doing a very good job of that. Next, we'll talk about that M-bit LCDU, so the stability of that feature to itself. So PLDC-MPC reduces error magnitude proportional to CD size on curvilinear features, even with dose contrast method. So the no MPC case shown before is using the PLDC dose contrast only, as opposed to dose contrast plus the geometry correction that the PLDC-MPC includes. We see a 22% reduction M-bit to M-bit. So this is how similar the M-bit is to itself if you overlay it, i.e. the edge placement error, M-bit to M-bit to M-bit. So we see a significantly better, more uniform contact for every curvilinear M-bit that we look at. This means that it's not just coming from the dose model improvement for LCDU. There's actual geometry benefits as well. Finally, we'll do a very quick forward look at high NA patterns. and the demands that they will have for the mask maker. So anamorphic will demand accuracy from curvilinear designs. There will be tighter pitches, which will result in worse LCDU. If curvilinear design increases process window, adopting curvilinear will be critical for the anamorphic format of high-NA. Those curvilinear designs will require MPC. So this is a slide shared by ASML at SPIE-AL in 2025. And we can see that as we decrease in pitch for a DRAM layer, we see a larger proportion of, we see a higher number of LCDU. So the smaller the pitch, the smaller the feature, the larger percent error that LCDU poses to your design, the more stochastic it becomes. Obviously, we want to reduce this as much as possible. And obviously for high-NA, this target on wafer doesn't represent a simple circle. It represents this ellipse on mask. So what does this mean for MPC? LCDU transfer from mask to wafer will be more critical even with Y stretching. So as we go from low NA to high NA, we'll have either a steeper slope or a change in offset of transfer, but we certainly don't expect high NA LCDU transfer to be better than low NA, even with the anamorphic Y stretching. So here's a quick thought experiment using this 16 nanometer wafer target circle. We have our design ellipse compared to no correction, compared to the bias correction, compared to PLDC-MPC. So these numbers are taken from the PLDC emulator we discussed further, and we'll just run this through a thought experiment of anamorphic stretch down to wafer. So here we can see that our dose variation band will not be improved from bias alone. So here's our dose variation band of no correction, which was 3.11. We saw that during our simulation. And PLDC-MPC went down to 2.59. The bias correction was 3.01. So we don't see a lot of improvement of dose variation band with bias correction only. We actually require the edge dose enhancement methodologies, the dose model portion of PLDC as well. One thing I'd like to draw your attention to on this slide is that when you bias the ellipse up to hit MTT in its midsection, you still see some elliptical shrink. So bias correction only isn't sufficient. You'll actually need to change the curvature at the tips. This is why offline MPC for true multigon is so expensive, is because you have to go through multiple spline iterations to arrive on the correct one post-simulation. I'd like to talk about eccentricity a little bit. How much does that loss of edge matter? If you look geometrically, does it matter at all? So the eccentricity of all of these ovals look roughly similar. For the design, you have an eccentricity of 0.86. For no correction, it's 0.88. And PLDC is 0.86 as well. So these all seem very close to the design. How much will it matter on wafer? On wafer, it's going to matter quite a bit. So we can see that our design wafer of 16 nanometer circles, our eccentricity of our no correction and bias correction is basically going to be almost exactly similar. If we use PLDC-MPC, that's the closest eccentricity to the design eccentricity of 0. This means that even a small loss of signal from the bias correction, as we saw previously, is going to matter quite a bit in terms of the ellipticity on wafer itself. This loss of margin is going to add up, especially a higher MEF. This is done just assuming a MEF of 1. We know it's going to be larger for a densely packed contact array pattern. So again, this is just a thought experiment. This is not a wafer simulation. It's just taking the simulated ellipse and using the anamorphic stretch to see what would the elliptical effects be like on wafer. In conclusion, PLDC-MPC provides a faster, cost-effective solution that meets Micron's requirements to implement MPC. We have begun qualifying PLDC-MPC into production to provide additional value to our customers, and we expect to see the benefit of PLDC-MPC in high NA pathfinding. Again, this has been a collaboration between D2S, NuFlare, and Micron. We would like to extend special thanks to all the personnel at Micron, NuFlare, and D2S that worked on this and provided support for this work. Thank you all for your time and attention.